box is what's being recorded. So it's only the portion of the screen that you're seeing there. Okay, everyone, it's been a long time since we were together. I need you to do some breathing exercises and to think about what we want to try to accomplish today. This is a short lecture in some senses, but it is an extremely important one. We do not derive the material balance equation in this course. We probably should, but frankly, I leave that to you. It's important that you recognize that the material balance is an exact accounting of whatever the system has in it. The general form of a material balance equation is given as you see over here. Usually it's written in terms of some rate and pressure relationship, and we can express it as such. It's then derived out as a full material balance equation. So the first and easiest material balance equation is for gas, and you can see that in this case there's no water influx for this case. This is simply a relationship of pressures and formation volume factors. Okay, the easy variables, if I may, let's see, I don't want to do that. Let me delete that, sorry. The easy variables, we measure the gas production. We have an initial pressure estimate from somewhere, don't know where, but we have one. The Z factor is automatically a function of pressure and composition, so it's available, that's there. So the key here is really estimating average reservoir pressure, and of course the Z factor comes from the average reservoir pressure, and then the objective variable is almost always going to be gas in place. So I'll stick that there, and sorry for the color scheme. There you go. So our objective is gas in place, and our key variable, if you want to call it that, is the average reservoir pressure. So very quickly, let me ask the audience, how do you calculate average reservoir pressure? How would you, what sort of equation would you write for average reservoir pressure? Let's pick someone at random. Before you pick yourself before I pick you. Okay, no volunteers. Santiago, you're the guy with all the experience. How do you estimate average reservoir pressure? Give me a hint. Speak up, guys. Okay, so you have a pressure buildup test, correct? How long is that pressure buildup test supposed to last? Okay, you're a clever boy, but what do I mean? I mean until the pressure stops changing. And that would be the average reservoir pressure. What would your manager say, Santiago, if you wanted to shut in a well for a year? What would he say if you wanted to shut it in for 6 months? Three months. 1 month. 1 week. Right. That's why in the literature you always see a 3-day buildup. Is 3 days enough to estimate average reservoir pressure, Santiago? No but. I like that. That's a perfect answer. No but. Not no space but no comma but. So what's the but? Okay, what happens if you use the average reservoir pressure estimated from a 3-day buildup? Is it too high or too low? And what happens whenever you use a pressure that's too low in this equation? Well, that was a good answer, but let's try again. Is G too high or too low? You want to guess again? It'll be lower, that's right. Because pressure is energy. And energy is related to volume. So if our energy level is wrong by being too low, our volume will be wrong by being too low. Okay? So everyone keep that in mind. There's a lot to be learned from the simple equation. The next is the general material balance equation taken from Dake, D-A-K-E. And what you notice is that there are all sorts of different terms. There are withdrawals of gas and withdrawals of water. You don't think about it, but water is something that's taken out of the system. And then there's expansion of the gas. And then there's expansion of the water and the pore volume. Okay, those things, the withdrawals we can calculate, right? We know how to measure the withdrawals, correct? Hello, everybody? Okay, and the gas expansion is simply a relationship between the initial gas in place and the change in formation volume factors, which is okay. And then we have the water and pore volume expansion or compaction, and you see that that's okay too. There's no real mystery there. The variable we're looking for is G as in golf ball, and that's there, and it's there. So this is going to be ugly, but not really bad. Everything else we can measure. Okay, what's the missing link? The missing link is water influx. What is water influx, class? That's very good answer. Now, how do I measure WE? You cannot measure WE. WE is the devil. You guys understand? The devil? Why is WE the devil? Avery, are you in the room? All right. It's an unknown function. It's a function of what? It's a function of time. Well, yeah, it is, but ultimately it's a function of time. Good point. Okay. But how do you measure this again, Santiago? You can't, right? So if you type into the SPE 1 Petro water influx, water encroachment, water drive, all those keywords, how many papers are going to come up? Like more than 10? More than 100? More than 1,000? That's correct. The last time I did it, it was about 750. So 750 papers devoted to this thing. Does that bother anybody? That's an exaggeration, but it sounds like something I would say. Thank you. You have learned well. Fundamentally, you don't know what the answer is, so you're poking at the problem. Name a method. Well, you could assume a functional form for WE. You could try to reverse solve it. You could use some sort of an optimization algorithm. What most people have done is they've assumed a functional form for WE, and then they wait and see if it works. We're not going to deal with this very much. I just want you to realize that WE is the devil. WE makes everything crazy. There is a way of getting around the water and pore volume expansion compaction. I'll talk about that a little bit. But the WE, that one's not going to come along peacefully. That one's really tough. There is no way to measure WE. Therefore, you must either assume a model or solve it some other method, like backwards. And I've seen every different type of contraption you can imagine trying to solve for WE. If you do it that way, then WE ends up being an error term. It ends up being something you don't know and you're trying to estimate, so all the error ends up going into it. Now, if we arrange the material balance equation according to Dake and the common form, we get something like this. And that doesn't look so ugly because what happens is we can start making things go away. If we assume there's no pore volume compaction or expansion, then we can ignore that term. If we assume that there's no water influx or water production, then we can ignore that term. And if we ignore these two terms, it takes us back to our good friend up here, the dry gas, no influx case. Now, obviously, all of these assume a dry gas formulation. There's not a compositional system, etc., etc. Just so you know. Everybody okay with that? Repeat after me. WE is the hardest part of this problem. WE is the hardest part of this problem. Okay, everybody, you said it mentally. Now, there are a lot of computer programs that have been written to resolve the material balance equation, because I started this lecture by telling you that material balance is exact. If material balance is exact, then the results that we obtain from it should be correct, except there's poor inputs. What are the poor inputs, class? What are one of the poor inputs? Well, the average reservoir pressure is the worst one, because that one's the most critical. We have to know it. Water influx, water production, pore volume compressibility, these are all very important. I'm not denying that. But we can't even start if we don't have the right pressures. Let me repeat that. We cannot start if we do not have the right pressures. So if we don't have the right pressures, what do we do, class? Stop. If you were here 50 years ago when these equations were being used, maybe 60 years ago at their height, and you suddenly realized there were parameters you didn't know and functions you couldn't measure, what would you do? And I want you to think carefully about this. You have to put so much information into a material balance equation that you may as well put it into a reservoir simulator. So material balance started to die off when simulation became popular. And in a way, it's cheating. We don't know the answer. So we'll just model any one of a number of scenarios. That's why today's lecture is short. We don't have to derive all this, although you should. But reservoir simulation essentially displaced material balance as a primary reservoir engineering mechanism. And when you read Dake, he gets really angry and upset about this. But there's not a lot we can do. So let's take a deep breath. We'll move on with material balance. Now, this is an analytical course. Why would we study material balance? Well, because material balance equation is still exact. And we need the material balance equation in order to solve certain problems. And we're going to do that in Thursday's lecture. Let me ask you a very simple question. Is everybody ready for a very simple question? Pick someone at random. Who wants to volunteer for this question? No. Today's the Korean day. Okay? Thursday will be the French day. Okay, Korean guys, I want to simplify the dry gas material balance case so that I can do something very easy with it. That's this case right here, the no influx case. How do I simplify it to make it really easy? What happens? Okay, very good. Assume Z equals ZI equals 1. What's going to happen when I do that, folks? Okay, but what happens to the material balance equation? It is an exact accounting. What happens when you make an assumption like this? I was at an SPE meeting the other day where a gentleman got up and he presented as his starting slide a picture of Mr. Death, the Grim Reaper. I always wanted to do something like that. Unfortunately, I don't have that luxury today, and probably you would ask about my sanity. But if you assume Z is equal to ZI is equal to 1, the ideal gas case, imagine the Grim Reaper, because you just killed your problem, whatever it is. How much error occurs by assuming the Z factor is equal to 1? Class? Well, unfortunately, there's no easy way to do this. God, I hate slow internet. You guys probably love slow internet. Can you see this? Can you see that chart? Okay, so you're assuming everything is 1. Is that a good idea? Imagine this is your bank account, Avery. Here it's 35 or 40% of what it should be. Over here it's 105% of what it should be. Over here it's 200% of what it should be. Do you get the message now? So assuming Z equals 1, is that a good thing or a bad thing, class? And we'll talk about this later on, but some people did that. They assumed that the Z factor was equal to 1 so they could develop a convenient rate equation. If the material balance equation is wrong, everything you do with it is wrong. I cannot overemphasize this. Okay, let's talk about oil. Is oil... Yes, sir. It does account for the material balance, but you specifically tell it there's an aquifer here. So you impose the solution on the problem. And then you turn the knob on the aquifer to make it give you a WE that matches the P over Z. Personally, I think, yeah, everything that you're saying is correct. You have to input all that information, and it should be valid. But you're not going to waste your time with a simulator trying to match average reservoir pressures. You're going to take your time with a simulator matching well pressures. That's where the really critical difference is here. Because everything about material balance is matching average reservoir pressures because we reduce the dimensionality of the problem to zero. There is no physical dimension here. It's merely an accounting of molecules. But a simulator has a multi-dimensional accounting. So when you apply a physical aquifer, and then you have pressures, not average pressures, but physical pressures at various locations in the reservoir at various times, then your goal is to try to optimize the properties of the system with the observed pressures. Excellent question. Excellent question. And one that cannot be overemphasized. The simulator has infinitely more flexibility than material balance because you can design the simulator to accommodate any condition. Does that make sense? So, okay, look around the room. How many people in the room have taken Dr. Moridi's simulation class? How many people have taken another simulation class? How many hands are up? 5 or 3 or 2? 0? What's the first thing you learn in simulation class? You must have material balance. You can't, you track it, and it better be something like 10 to the minus 10th percent or 10 to the minus 12%. So a fraction of a billionth of a percent, that sort of thing. Am I in the right ballpark here, people who specialize in simulators? This is something that's printed out. They check it all the time because you're absolutely right. Your simulator cannot leak. It cannot create or destroy mass. So that has to be accounted. Excellent questions. All very good. Okay. The next is the oil material balance equation. And the oil material balance equation for constant compressibility oil above the bubble point, which is the lazy case, is here. Okay? And again, these are the things we can measure. We can measure BO over BOI. We can measure NP. We can measure CT. We can measure PI. And then therefore, the only thing we've got left is N is our variable that we're after. And here I'll make a little cloud. P bar. It's not a very good looking cloud, by the way. Okay, so there's our cloud for P bar. I have to move it over a little bit. Okay, so N is our objective, and P bar is the mechanism to which we get there. Let's run a really quick test. What do you think the recovery is going to be for a black oil above the bubble point? Anybody want to guess? Very good. How did you know that? Correct. So all you have to do is solve for NP over N, substitute PI and P bar, you can make P bar be 0. You multiply that times CT, you can assume BO over BOI is 1 or something close to that if you're lazy. And that usually turns out somewhere between 5 and 10%. So you only have enough energy in the fluid to produce less than 10%. So how do you get the other 95% out, class? You have to add energy to the system. Okay, then we have the generalized solution gas drive case. This is the one where we have like a Coca-Cola type liquid where it's being driven by the gas. And all of this looks fancy, but it's not. You have a withdrawal term. Again, you have our good friend Mr. Oil and Mr. Water. And then you have the expansion term for the oil primarily. And then you have this silly gas cap term. Sorry about that, but it's in here. The gas cap ratio is M as in man. That's basically the volume of the gas cap over the volume of the liquid. And then you have the water expansion, pore volume expansion term here, just like you had for gas. And then you have the devil again. There he is, just waiting. Okay, so if we set up all of these equations, we still have to measure everything, and the weak link is still pressure, but we also now have to measure solution gas-oil ratio, and we have a whole bunch of other PVT properties here that we have to measure. All of those can be obtained from correlations. This is not an impossible equation to apply. Because of the gas expansion, the water expansion, and the gas coming out of solution, which is part of the oil expansion, the recovery factor for this particular drive is much higher. It's usually 15 to 35%. So as opposed to the upper equation, which is about 5 to 10%, this could be 15 to maybe even 35%. You're still leaving 65 to 70% of the oil in place. How do you get it out? Again, you have to add energy to the system to do that. Okay? And again, identical to our comments for the gas material balance case, the simulator has removed all of these constraints because of its flexibility. This is a zero-dimensional mass balance on the system. Once you move to a simulator, you can match things at different points in the reservoir, and you can tune the model to represent that. Okay, so let me go on and get out of the objectives and talk about, these are some notes that I had from a short course. Probably the most important thing you need to remember about material balance is all inflows and outflows are accounted for. The average reservoir pressure is required, and you must have the rock and fluid properties at some scale. I'm going ahead and do this for you. Okay. Now, we don't see a lot of oil material balance. I'm not sure that anybody in the room is going to understand why, but we just don't have the mechanisms of measurement. But for gas, we oftentimes see volumetric dry gas material balance. We see abnormally pressured reservoirs, and then we see water drive, water influx, and so we use a model. The most important discussion we can have today is that material balance yields reservoir volume. That's it. It doesn't give you permeability. It doesn't give you porosity. It doesn't give you any of these other things. It gives you reservoir volume. I know you're tired of hearing me talk. We've been doing this for 30 minutes, but let's go through it again. You must have all inflows, outflows, and generations. You must have accurate average reservoir pressures. you must have rock fluid properties. Now, the people who are simulation people, what does this sound like to you? It sounds like a simulator. And that's exactly the problem with material balance, is it was displaced by the simulator. How come we don't use rotary dial phones? How come we don't use 30-pound laptops? Because things got better and we're able to use other products now, other technologies now, and essentially the material balance got replaced by the simulator. However, we are going to use material balance in this course. We're going to use it in the next lecture. You're going to have an assignment on it. And speaking of which, I am going to do my damnedest to get all the assignments out by the time I leave, which will be the 28th. Okay? Any question about material balance philosophically? This is your chance. Any questions about material balance philosophically? Very good. Okay, so here's the concept of a material balance. You have the before and you have the after. And what you notice is you have a gas zone. Not a lot changed there. Not a lot changed there. You have the connate water, which is the immovable water in the gas zone. Sorry, this thing doesn't like drawing on top of itself. And it expands a little bit in the gas zone. Then you have the oil zone. And what happens in the oil zone is that you produce oil. That's the whole way we make money. So you produce oil. And the gas component gets bigger. And then the connate water expands. That's the in situ water. And the rock expands. No problem with that either. And here, as we talked about before, is the evil one, the encroached water, which is another name for water influx. So before, we had a relatively simple system. Afterwards, we have a whole bunch of things. We have water expansion here, water expansion here, rock expansion here. We have water encroachment. We have the production of oil, the generation of gas. In this particular view, the gas zone didn't change very much, but that's fine. So you've got to have accurate volumes. And when I say volume, I mean mass. You must have accurate quantities of production. You must have accurate estimates of average reservoir pressure. You must have accurate PVT data. And again, if I'm wearing you out with this, if you've got all of this, you really have a simulator anyway. So you're going to have reservoir properties, which are saturation, formation, compressibility, etc. as well. Okay, now this is a real case, and the way this works, this particular field, which was the Schuler field, this is in 1944, and of course the war caused them to go nuts with the development of this field. But the original development is shown here. Let's use our friend Mr. Cloud. And then our next development, which was only about, 6 months later, they perforated this thing like a pin cushion and drilled a whole bunch of wells in it. And then by about a year later, in 1942, sorry, I've got this all wrong. This is 40, 38, 40, 41, and you can see they just keep mapping the pressure profile, and then they keep adding wells. So from the 15th of February in 41 to the 25th of July in 41, you can see the difference. I may have these things placed incorrectly, Bart. Sorry about that. But then you can see in December of 1941, you have significant depletion that is given by these isobars. And then in November of 1942, you have even more depletion shown by these isobars. They're measuring pressures. I remind myself to go back and make sure I didn't represent that wrong. So how do you get the average pressure in this field? Anybody? Santiago already said that you have to take shut-in pressures, and you can see the shut-in pressures are listed, the little numbers. But we have to take the shut-in pressures and somehow come up with an averaging formula based on volume. So we have to know the volume associated with that pressure measurement. That's impossible. Go ahead. Sorry? We'll use the production cumulatives, but that's correct. We'll assume it's pseudo-steady state, which we haven't talked about yet, but we'll assume that we can average the pressures based on cumulative productions. Thank you. So you'll take the cumulative production at a well, multiply it by its pressure, divided by the total cumulative production, add those up, and that would give you the average reservoir pressure. Okay. And I guess the last thing I'd say is this is not going to be a fun process of estimating the average reservoir pressure. I think we all see that. This is an example of a field data set. I don't want to bore you with the details, but I will. This is the pressure profile. I have no idea how they average these pressures, so don't ask me. I'm assuming they knew what they were doing. Now the pressure goes back up. You won't see that again in this lifetime, so you better get used to that. How did the pressure go back up, class? Not injection. Correct. This is water production that I'm marking, but it just comes on like gangbusters. It's almost exponential. And then they start fooling around with the field, I guess. They probably took no, they didn't take any wells offline. They must have been doing something else, probably some water management. But you can see that the pressure's actually stabilized because of that. And you can see also, here's the oil rate. You have a plateau, which is a famous feature. And then you have this declination. And I've drawn in a line, I know that. That would be sort of a declining feature. And it roughly corresponds to the decline in the pressure. And of course, then when the pressure flattens out, the rate drops. If you'll look over here, this is the number of wells. This is a common plot. You probably want to do this in your own experience as well. Is chart the number of wells versus time. That's the number of wells. I should change this probably to some other color. What's your favorite color? Don't say green. Green's for oil. You guys didn't miss me while I was gone, did you? Did I mention that I did 4 things back to back? Don't ever do that. You don't have to listen to me, but you probably will live longer and be smarter if you do. Don't do what I do, but do what I say. How's that for a parent? Okay, so oil, water, pressure, number of wells. I'll leave the GOR alone, but you can see that what happens is they're managing the pressure in the GOR, and the GOR starts to drop when the water influx comes in. You've got all the functions here. Everything was measured. There's my mouse. There it is. I can't see. Where'd you go? There it is. I've gone ahead and assumed that the average reservoir pressure is correct. And I'm going blind. Okay, there it is. Okay. So now you just take this information and put it into the material balance equation, and you have an answer that pops out. Not exactly, but sort of. Okay, so returning to our discussion before, I'll cover this very quickly. We have the Blackwell material balance equation. That is for pressures above the bubble point, and we have the solution gas drive material balance equation, which is valid for all pressures. And you see there's a fundamental difference. Above the bubble point, we're not going to recover very much. Generally speaking, it'll be somewhere on the order of 5 to 10%. Below the bubble point, in theory, on a solution gas drive case, we may be able to see as high as 35%. Okay. For gas, there's a little bit different rendering. I've gone on ahead and shown the general material balance equation here. When you start knocking things off that you don't like there's no gas injection, there's no water production, there's no water production again. Not that you would do this, but there's no water injection. And of course there's no water influx. Then they all die off. And then if you decide you also want to kill the abnormal pressure term, or what we call the rock and fluid expansion term, it's here. You do that, you get the simplified equation here. Okay. Fekovich, Whitson, and Reese gave this equation below. It's essentially the same as the equation above, as the top equation, but they gave some components here. They wrote some volumetric terms for the aquifer. That's about the only difference they gave. They also defined something called the cumulative compressibility. Rather than looking at the instantaneous compressibility, they talk about the cumulative compressibility. That's okay. That's not really all that important. What is important is understanding that when we have an abnormal pressure case, there's going to be a signature that you're going to see. What does this signature tell you the relationship for the dry gas case is? It's a straight line. If you plot as the y-axis P over Z and you plot as the x-axis GP, you'll have a straight line. If you have an abnormal pressure data set, then it will not plot as a straight line. So right out of the box, I'll show you this is a simulated case, and unfortunately a student made it a gigantic reservoir, but it is nonetheless a simulated case. There's a straight line extrapolation, and it comes down to here. You'll notice that I put this equation out here, and I've said that there's a GP squared term, and that GP squared term is 0. There's a reason for that, and that is that the governing equation for abnormal pressure is a quadratic cumulative production relationship. I've attached the presentation for this, or I put it on the server as an extra presentation. It's a student thesis that I did about 10 years ago, and we explain how to derive the formulation for abnormal pressure as a gas production squared term. So if everybody's comfortable with this, this is how the simplified volumetric gas reservoir case is going to look like. This is a simulated case. It's a volumetric reservoir, and you would expect to get a straight line performance. Okay, deep breath, everybody. Ready? Here's what happens whenever you go to the real world. Now, fortunately, this Anderson L case, it's a single well and a single fault block, in South Texas. So we assume that all of the non-ideal behavior is due to what? It's due to abnormal pressure effects. Can somebody tell me what the extrapolation is out here? No, what's the number? Is it about 120, maybe 117? We call this G apparent. So we're saying that the apparent gas in place is approximately 117 BCF. Of course, I'm extrapolating this to here. Sorry I didn't make the graph bigger, but it's free, so don't complain. You guys don't complain that much anyway, actually. So this would be the 117 BCF approximately right there. What's the real number? We think it's about 74. So if I go to Excel, and I say equals 100 times 73.5 divided by 117, I get 63%. Okay, who in this class wants to get rich? Somebody must. Turnpon, who's raising their hand? No one. What, I have a bunch of religious crazy people who don't love money? That's great. This is the first time. Okay, let's pick on somebody. Let's pick on one of the French guys. Is any of the French guys there? Who's there? Ralph is there? Okay, so you come to me and I'm your banker and you tell me you're going to recover 120 BCF and I give you enough money to develop this field. And then you come back to me and you say, I only produce, or I can only account for 64% of the mass in this field. What am I going to do as your banker? Sorry? Well, what's a banker's way of doing that? I'm not going to loan any money to you again. And probably I'll sue you. Because you just cost me 35% of my investment. How did this happen? How did we discover abnormally pressured gas reservoirs? Why is there an apparent straight line? Anybody? So what actually happens here is that the gas is supporting the overburden. These are all overpressured gas reservoirs. So the rock matrix is inflated due to the gas. So whenever I produce the gas, eventually what's going to happen? The rock matrix is going to collapse slightly. Collapse is a bad word. It's going to rearrange. Imagine stepping on a balloon that has inside of it something that has structural integrity. Until the system leaks out a little bit, you're going to assume that the volume or the mass of the system is represented by the balloon. So imagine now that you have pores which are overinflated with fluid, and you produce that fluid. And you can see that mentally there's a switch point. There's a switch point about right here. After which you could draw a straight line that extrapolates. I'm not doing this very well, am I? Something like this. And this is actually what the first student tried to do. So it was a two-step extrapolation with a switch point. And I'm going to move the switch point here. And ironically, even though the first student saw this and created a methodology around it, this had also been observed in practice 20 years earlier. Somebody wrote a paper and said that this was the hydrostatic switch point, that at this point it's hydrostatic pressure. But you know, things in nature, they usually don't happen as sharp fronts. So what I did is I sat down with a student and we derived this methodology where the pressure behavior is actually a quadratic. So you don't see a sharp point here, you don't see a sharp switch. You see a decay like this. Okay? So that's abnormal pressure. How important is abnormal pressure in your life? Where's the French guys again? Where do you want to work? I never heard of don't know. What country is don't know? Is don't know Gabon? Is don't know Angola? Is don't know Senegal? What is don't know? Brazil. Now let's say it's West Africa. Why West Africa? Because this is a feature that occurs in very immature sediments. Is the Mississippi River Basin an immature sediment basin? Yes. It's dumping billions of tons a year of sediment into the Gulf of Mexico. These sediments do not have time. The sediments in the Gulf of Mexico are young. They don't have time to compact. This is an incomplete compaction phenomenon. It happens in West Africa. It happens in the Mississippi. It's going to happen in the Ob Gulf region in Russia. It's probably going to happen in offshore deepwater gas, etc. Anywhere where you would expect to see a lack of consolidation, you're probably going to see something like this. Okay? And they discovered this, of course, by accident, as always, in the late 1960s in the Gulf of Mexico, because they were predicting much higher recoveries than they were actually getting from their gas reservoirs. So that's the practicality of abnormally pressured gas reservoirs. Okay? All right. You've seen enough. Now let's talk about water influx. Now water influx is completely different than abnormal pressure. In the case of abnormal pressure, you have what appears to be a normal pressure line, and then you have a secondary line that comes in like that. In the case of water influx, it looks like This is the correct trend, by the way. And then it looks like you've got a straight line here. And what can you tell is going on here? What is this a function of? The permeability of the aquifer here, the permeability of the aquifer here, permeability of the aquifer here. If the aquifer is strong enough, what will happen? Why? It will totally recharge the system. Now, in nature, that's probably not going to happen. But in these simulated cases, it can. How can you tell the difference between abnormal pressure and water influx? It's a trick question. I don't know either. With a lack of information, I don't know how to tell you to do it. Anybody got any ideas? Do you notice that over here, you have what appears to be a nice decay, and then it makes a fish hook. How do you say fish hook in French? You know fish hook? Okay, so there's a fish hook in this. Now, one of the things that happened is there were some guys that sat around trying to figure out how to make money when there was a credit for natural gas back in the late 1970s in the United States, and that credit was what? It was almost $10 an MCF at that time. So what happens is the solution actually just stops. It just dies. So what they determined was if they could lower the pressure in the system, then they could dewater this and they could actually produce much more gas. Is that a good idea? And I'll remind myself to put Agarwal's thesis on the server as well. Is it a good idea to try to dewater an aquifer and produce more gas? Hello? Yeah, you have to produce the ocean, and then where are you going to put the water? So number one, you have to have essentially free water production. It has to come out in huge volumes. And number two, you have to be able to dump it for free. If you don't have both of those characteristics, you're not going to make money with this. So tell me something. Can you dump produced water in the ocean? Not in the United States, you can't. Not in most countries you can't. And I know what you're thinking. Well, it's not even as saline as the seawater. Yeah. But dumping an ocean of salt water into the ocean is not going to be acceptable. They had actually construed an idea of running a pipeline 50 miles offshore and just letting it vent in the bottom of the Gulf of Mexico. What would happen if you tried something like that now? You'd be shot. So the idea that you can produce vast quantities of extra gas from water drive reservoirs or water influx systems, forget it. It's not going to happen. Okay, I think I'll stop there and let you follow up on the rest of this. Are there any questions or discussion comments? Do you feel like you got your money's worth on this hour of power? Okay, so on Thursday we'll talk about pseudo-steady state. It will be the basis for a homework problem.